Hello, welcome to Open Logic. In this video, we're going to construct a multiplexer and demultiplexer by using logic gates. This is an AND gate. If both the inputs are 0, then the output is 0. If this is 0 and this is 1, the output is still 0. If this is 1 and this is 0, the result is the same. Only when both inputs are 1, the output becomes 1. While this is perfectly captured in the truth table, it doesn't really illustrate the practical usage. Let's color code the signal by intent. The blue is a data line and the red is a control line. The behavior hasn't changed. When we set the control line to 1, the output is 1 when the data is 1, and the output is 0 when the data is 0. Or in another word, the output will follow the input data. If the control is set to 0, then the output will become 0. Practically speaking, the input data does not propagate to output, and as such, AND gate behaves like a signal filter. Now, let's say we have two AND gates as signal filter. We can control them both together by simply connecting the control signal as 1. When we have data coming in, they can only pass through the AND gates when the control signal is 1. Now say we put a NOT gate here. This becomes a very interesting setup. This allows only one of the AND gate to pass through its data. Say if the control is 0, then this AND gate is enabled and this one is disabled. If the control is 1, this AND gate is enabled and this one is disabled. And practically we have created a selector. Using the same method, we can easily extend the functionality to more than 2 data lines. Say there are 4 data lines, we will need 2 control lines to control the 4 AND gates. These are the 4 data lines and these are the 2 control lines. Now we can put unique sets of NOT gates to each of the AND gate. For example, we put 2 NOT gates here and therefore only 0, 0 can enable this AND gate. We put a NOT gate here so that this is enabled by a 0, 1. We put a NOT gate here so that this is enabled by a 1, 0. And this one here does not have any NOT gate, and it is enabled by 1, 1. You see the control lines here behave like an address. Its value indicates which AND gate to be enabled. Now, if you pay attention, only one of these outputs is active. The rest remains 0. And so we can put an OR gate here, and thus we have created a multiplexer, which is a many-to-one selector. We can also create a one-to-many selector. It's even simpler than the multiplexer. All you need to do is connect all input data together, and this is a demultiplexer. While these two components may seem simple, they are very versatile and probably are some of the most important components in the VLSI design. Let's look at a few examples. A design may have many config status registers. Let's say we have 256 of them, and each of them is 32 bits wide. First, we don't expose these registers to the design top level. That would create a lot of pins for the design. Instead, we use a demultiplexer, where it has one 32 bits input data and one 8 bits input address. The 8 bits address supports 256 combination. It can channel the right data into its designated register. To read from a register is the same. We use a multiplexer to channel a register data onto a read data signal. This structure helps to maintain the register's number. For example, you can have a 10-bit address to manage, say, 900 registers. Now you have extra margin to add registers in the future, since the 10 bits address are not fully utilized. Another usage of a multiplexer is in calibration. Say you have a receiver and it receives a clock and a data. In reality, the clock and the data may not be aligned, and therefore you need the capability to calibrate them so that you can sample the data correctly. By using multiplexer, we can connect a signal to all of its inputs. At this path, we add a delay component. You can see that this path has no delay. This path has 1x delay. This path has 2x delay, and this path has 3x delay. Now by using this signal as a code, we can introduce delays systematically to a signal. For example, we can now delay the clock here, so that it always samples the data at the middle. Here's another example, programmable logic. This is a multiplexer. Say we hard tie the input to these values. If we put 0, 0 at the control line, this input is selected and the output becomes 0. If we put 0, 1 here, this input is selected and the output becomes 0. If we put 1, 0, this input is selected and the output becomes 0. And finally, if we put 1, 1, this input is selected and the output becomes 1. If you pay attention, this really is one AND gate. You may think it is ridiculous. Why bother using multiplexer when we can just use AND gate? Now imagine if this is memory element where we can program its values at will. If we set the value as 0, 1, 1, 1, this circuitry behaves like an OR gate. If we set the value as 1, 1, 1, 0, this circuitry behaves like a NAND gate. And thus we have created a programmable logic. Now these three examples are overly simplified. For example, this is not a standard FPGA logic cell, and the real calibration circuitry is way more complicated. But nevertheless, these examples, they should provide the right fundamental concept. Alright, that's all for this round. Thank you for watching. And before we go, don't forget to like, share and subscribe.